Okay guys, let's go ahead and work on your 8-7 notes today. Today we will be factoring special cases of trinomials. These two special cases are 1, perfect square trinomials, and 2, the difference of two squares. Now just to warm up, let's go ahead and recall the shortcuts for these special cases. First, if we have a plus b squared, that's going to work out to be a squared plus 2ab plus b squared. The next one is very similar. A minus b squared is very much the same, except we have a minus right here. A squared minus 2ab plus b squared. You'll notice two similarities. They both have a squared. They both have b squared. They also both have 2ab in the middle, but because this plus changes to a minus, this plus changes to a minus. And finally, we have a plus b times a minus b works out to a squared minus b squared. These first two right here are both examples of what we call perfect square trinomials. They're perfect squares because they're equal to something squared, and they're trinomials because they have 3 terms. This one right here we call a difference of squares. We call him a difference of squares because difference means minus, so we have a minus sign, and we have 2 squares. And that's what we'll be working with today. So in our previous lessons, we started with our factors, and we found out what they equal to. Today's lesson is we're going to start with our trinomials, and we're going to work backwards to get us their factors. So we're going to go that way. So in our previous lessons, we multiplied these binomials together. And factoring is like multiplication, but we're going backwards. So we're going to use these shortcuts backwards today. So first we're going to figure out how to recognize when we can use these shortcuts. So a perfect square trinomial is always going to be something that looks like a squared plus 2ab plus b squared. You'll notice that the first term and the last term are both perfect squares. This means they're equal to something squared. A squared is a times a. B squared is b times b. That's what it means to be a square. And then the middle term is 2 times their roots. So the root of a squared is a, the root of b squared is b. So you have 2 times a times b. So that's a perfect square trinomial. Next, our difference of squares is where you have 2 square numbers and you take their difference. You subtract them. So that's a squared minus b squared. Here, the first and last terms, just like in a perfect square trinomial, are perfect squares. Because a squared is equal to a times a, so it's a squared. And then b squared is b times b, which is b squared. Now, instead of having a middle term of 2ab, they don't have a middle term. Instead, there's a minus between them. There's a minus sign. That guy right there. So that's a perfect square trinomial and a difference of squares. Today, we are going to factor each one of them by doing our warm-up backwards. So factoring a perfect square trinomial. First, let's check that this is a perfect square. So we're going to write our first term as something squared and our last term as something squared. M squared, well that one's pretty straightforward. That's m squared. And 49 is 7 squared. So the first and last terms are squares. Awesome. Now we want to find out, is our middle term equal to 2ab? Well, our a is m, and our b is 7. So that means 2ab is equal to 2 times m times 7, which is 14m. Is our middle term equal to that? Oh yeah, 14m, sure enough. So this is a perfect square trinomial. Cool. So a term is m, our b term is 7, so we can factor that by going m plus 7 times m plus 7. Oh wait, that's just m plus 7 squared. Nice. So our process here was we looked at our first term. Is it a square? And our last term, is it a square? Yes, they were both squares. So then we found if our middle term equaled 2 times their square roots. And it did. Nice. So we have m plus 7 squared. Okay. So go ahead and try to do b by yourself. Remember our steps is we want to write the first and our last term as squares, and then you want to see is the middle term 2ab, and then you can write it as a plus b squared. Let's go ahead and pause the video, try out b. Okay, here we go. Let's rewrite this guy. Well, n squared, that's n squared, and 36 is 6 squared. So that means our a term is n, our b is 6. Now we want to find out, is negative 12n equal to 2ab? Well, 2ab in this case is 2 times n times 6, because a is n and b is 6. That's equal to 12n. Oh no! We have a negative 12n and a positive 12n here. Maybe we considered something wrong. Could it be that 36 is also equal to negative 6 squared? Oh, that's true. So our b term is not 6, it's negative 6. That means this is 2 times n times negative 6, which is a negative 2n. So it's very important to remember that this can be positive or negative. So now that we know our a is n, our b is negative 6, then this is equal to n minus 6 quantity squared. And finally, let's check out number C. Check out example C. Remembering your process right here, check the first and third term. Are they squares? Is the middle term equal to 2 times the roots? If so, then write it as a square. Go ahead and pause the video and try out your skills. Okay, let's go ahead and get started. 4p squared is equal to 2p quantity squared. This is because 4 is 2 squared. So we can rewrite this whole thing as 2 squared times p squared, and we pull out that square to get 2p squared. Now 25, that's 5 squared. Awesome. So our a then is 2p, and our b here is 5. Awesome. So let's go ahead and write our a plus b squared is 2p plus 5 quantity squared. Now what if we're not sure we're right? How can we check our work? I'm so glad you asked. What a brilliant question. Well, we can check our work by squaring 2p plus 5. Is it true that 2p plus 5 plus 2p plus 5, 2p times 2p plus 5 equals 4p squared plus 20p plus 25? Let's find out. It's 2p times 2p plus 5 plus 5 times 2p plus 5 is 4p squared, that's a good sign, plus 10p plus 10p plus 25, and that's equal to 4p squared plus 20p plus 25. Sure enough, we did it right. So that's how to factor a perfect square trinomial. Now, like I said in our objective, we had 2 tasks to accomplish today. We factored perfect square trinomials. Now let's factor a difference of squares. So here in example 2. To see if we can factor a difference of 2 squares, we first need to make sure, is this equal to something squared? Well, that one's pretty straightforward, right? That's equal to q squared. Now 64, is that something squared? Yeah, 64 is 8 squared. Cool. So our difference of squares follows the pattern q plus 8 times q minus 8. That's it. That's how you factor a difference of squares. Now let's check our work. Is that true? So that's going to be equal to q times q minus 8 plus 8 times q minus 8. Well, that equals q squared minus 8q plus 8q minus 64. This plus 8q and minus 8q cancel out, giving us q squared minus 64. Oh hey, that's what we started with. We did it right. So again, to use difference of squares, all we have to do is make sure we have a square minus another square, and then we write the root plus the other one, and then the root minus the other one. Go ahead and try B. All right, let's see how you did B. Did you get r plus 10, r minus 10? If so, you did it right. If you got, straight up, if you got r minus 10 times r plus 10, that's fine as well. That also totally 100% works. Good job. In case that's not what you got, well, let's go ahead and explain. So r squared is r squared. 100 is 10 squared. So that fits our pattern of difference. We've got a minus of 2 squares. So we plug it into our formula of a plus b, a minus b, giving us r plus 10, r minus 10. Because here r is our a term, and b is 10. So to follow a plus b, a minus b, we do r plus 10, r minus 10. And lastly, following that same process, go ahead and try out number C. Here, the square root of 9s squared. Well, 9s squared is equal to 3s, quantity squared, and 16 is equal to 4 squared. So that gives us 3s plus 4, 3s minus 4. So as you can see, oh, I didn't put it in the box. So as you can see, all we've been doing today is our warm-up backwards. We saw something in this form, a squared plus 2ab plus b squared, so we know that that's equal to a plus b quantity squared. Similarly, if we start out with a difference of squares, we know that's equal to a plus b, a minus b. Now let's go ahead and look at example 3. Now, in example 3, you might not know what to do at first. You might look at this and you might say, well, 80, that's not a perfect square. Shoot, what can we do? Can we even factor this? Of course you can. Let's look at what they have in common and see how we can break it up. So I look at 80 and I look at 45, and I know they are both divisible by 5. So I can factor out 5. Now 80 divided by 5 is 16. And 45 divided by 5 is 9. And then I look at this and I say, oh wow, 16 and 9, Those are both squares. That cannot be a coincidence. And of course it's not. So that should have a little alarm going off in your head. This must be a difference of squares. Let's see if it's true. Well, the square root of 16v squared, that's 4v quantity squared. And square root of 9, well, 9 is equal to 3 squared. So we can rewrite this whole guy as a difference of squares. So that gives us 4v plus 3, 4v minus 3. So that's so cool. Of course that's so cool. But don't forget about our 5. We need to keep our 5 out front. So to factor our whole expression, we have 5 times 4v plus 3, 4v minus 3. Similarly on B, what's our approach here? What do they have in common? They both have a 2 in common, so let's bring that 2 out front. That gives us w squared minus 1. W squared minus 1 looks pretty simple, but it can get even more simple. We can factor it. Why is that? Well, let's look at w. W squared, that's w squared. And 1 is 1 squared. We actually have a difference of squares on our hands right now. Awesome. So we can factor that difference of squares as w plus 1, w minus 1. Remembering our 2 out in front, we have completely factored this expression. Awesome work. And that's it. If you ever wonder, shoot, I don't know what to do here, just start out with a little baby step and see where that baby step takes you. Okay, so today we factored differences of squares. We factored perfect square trinomials by putting this knowledge into practice, but backwards. I hope you enjoy the rest of your homework.